In this final lab, we took it upon ourselves to use our knowledge from previous labs to find coefficients of kinetic and static frictions, and we did so by creating our own individual setup and procedure. So, some of the recent literature, at least from what I understood from this 2020 paper, it of course confirmed that static friction is higher than kinetic, and it emphasized how certain surface conditions, for example, like lubrication, can affect both coefficients. And really, this has a lot to do with railroad braking and how it's important that there's an accurate modeling of static friction, for example, to ensure safety. So for a syringe, when you push the plunger, um, you often need to push against it using a bit of force because it is touching the inner barrel. And in the case for why I used a knee joint for kinetic is because when we're walking or we're bending our knees, although we do have synovial fluid around that cushions, the surface of our thigh or lower leg bones, they still do slide past each other as the joints move.
The materials that were used for this experiment were the Pascal/Capstone application software. The software is used for the creation of the graphs that will be displayed later on in this presentation. A triple beam balance scale to measure weight in grams, an air track that was used to slide objects in this experiment. It was the cart, and it was used to create a collision. A 250-gram block was used to add weight and increase the friction force, and a wood stopper was used to create friction.
For the procedure, firstly we measured the weight of the cart along with the added weight and wooden block we would be using for friction and incline. Then we made sure the system was working properly and set up properly before beginning the trials. For the first trial, the cart was pushed on its own with no friction or incline. For the second trial, the extra weight was added on top of the cart, and the wooden block was put in front of the cart for friction before being pushed. For the final trial, we put the track at an incline and pushed the cart there. After that, we calculated static friction and kinetic friction for all three trials and averaged them all, along with calculating any percent errors found within the trials and within anything else.
So this is data and data analysis for our final lab, Lab 9. To begin the experiment for our final lab, we did have to move twice because the sensors, even though it was turned on and the Bluetooth was on and we had the correct sensor number, they weren't connecting. When we finally got to the station with the sensor, did connect and was up and running, we were able to set up for our graphs. The design we decided for our experiment was to pick the red car and a wooden block to set on the track, and then from there move the red car from one space or from the start to the end so that way we could record the graphs. And then we use the formulas. F, which is friction, which could be static or kinetic, depending. Static is just when the object does not move, and then kinetic when at least one of the objects is moving. So the red car was moving. And then equals mu, which is the coefficient of friction, times our normal force, and our force perpendicular to the surface of the contact. So the force perpendicular to that would be what's pulling it down, which is our gravity. And then our normal force, the way we find that, is our mass times the gravity. So we had the mass of our car, which was 234.3 grams, which we turned into 0.2343 kilograms. Okay, so for our data of our Lab 9, we created our first graph, which is here. We did split it into 3 different graphs. So our original was our position, which is our red graph. It just shows the simple curve that increases, goes as the red car is going to the right. Our middle graph is our velocity, and then our third graph on top, which is the green one, is our acceleration. So all of those were made based on our position versus time graph that we had original from the movement of the red car and wooden block down the straight air track. And then we position 2 points, one at the beginning, as close to zero as we could get, but still be the start. And then one towards the middle, which was the actual movement, which we used to do our kinetic, because our kinetic is the actual movement. And then our static is before any movement. So you have to overcome our static in order to get kinetic energy. And so for our first point on the graph, for our velocity, our velocity was 8.084 to the power of -4. So it was very, very small for our start of velocity. And then for our increase, or once it's moving, and you can see like the start of the movement was 0.046 for our velocity for our first trial. And then this is our graph for our second trial. Again, we focused on our velocity graph. So our first point was -0.001. And then our second point, which again, when it started moving, was 0.19 for our velocity. And again, our velocity is our blue graph right there in the middle. And then this is our data for our last trial and our last graph. And again, we focused on the velocity one, which is the same place, the blue one. We started at 0 for our static, so 0.000 velocity. And then for our movement, we got a 0.049, our velocity. And then that's what we used to find our coefficients, both of static and kinetic friction. Then finally, our data, we went ahead and collected it all and created this table based on all the points that we had gotten from the velocity from the previous graphs. We did do two tries, so one with velocity and one with our acceleration. We did use the mu equals P over mg. So our mu is our coefficient of friction, equals P, which is our applied force or the friction force itself, over mg, which is our mass times our gravity. And our gravity is constant on Earth, so it's a -9.81. And we used that equation because our object, which was our wooden block, was being pushed by a red car by a force P. And since it went from not moving static friction to actually moving kinetic friction, we were able to get the constant velocity using our graphs. And then we decided to use that formula because that best fitted our experiment. So overall, our friction will equal our force P. And so then we used our velocity specifically points to find the coefficient of frictions both for static and kinetic. So for our trial one was 0.008. For our static and kinetic was 0.046. For trial 2, our static was negative 0.001. For our kinetic was 0.019. And our trial 3 was 0.000. And our kinetic was 0.049. So our averages of our static was 0.0023 and our kinetic was 0.038. We also, since we had the acceleration graph there, we went ahead and did the same values from the same points. We got those values and did the separate table, and we were able to find our average static acceleration coefficient, which was 7.14 to the power of negative 5. And then our average kinetic coefficient was 3.87 to the power of 3. So our coefficient of friction equals the force of friction over the normal force. So our force of friction was the velocity that we had gotten, because once it started moving, our velocity, it created a friction. So it was our kinetic friction, but friction nonetheless, over our normal force, which is just the mass times gravity.
In this lab, we measured the static and kinetic coefficients of friction and saw how friction affects an object's motion. When we repeated each trial 3 times, it helped reduce random errors and gave us more dependable averages. We learned how different setups, like using acceleration or velocity, can calculate friction and how sensitive these measurements can be. We also collectively contributed by helping decide which method gave us the clearest data and discussed how to interpret the sensor graphs. And overall, the experiment showed the importance of careful measurements and repetition when determining friction coefficients. Thank you.